Greetings of the day. Welcome to INFOCOM 2023. I'm Shravani Kurma. I'm here to present our work on RAS empowered mobile edge computing for URLC systems with digital twin driven architecture. I'm from IWIC Lab, National Sun Yat-sen University in Taiwan. Here are the contents of this paper. First, we'll start with the introduction, then we'll cover the system model and proposed solution. Later, we'll walk on our way towards the results and discussions, followed by the conclusions and bibliography. Here we go with the introduction. In this slide, we'll discuss the importance of different technologies in realizing the potentials of metaverse and overcoming some of the challenges it possesses. The metaverse aims to blend physical and virtual worlds, enabling the users to seamlessly move between them. However, there are significant challenges to deploy metaverse on the large scale for low-cost mobile users, including energy inefficient, extensive resource interactions. To overcome these challenges, we need to consider technologies like digital twin and mobile edge computing. So, what is meant by digital twin? Digital twin is a virtual replica of the physical object or system, and it can be used to simulate the behavior of the physical world, allowing us to minimize total computations and end-to-end latency. And coming to the part of mobile edge computing, it is nothing but a network architecture that brings computation and data storage closer to the end user. By using MEC, we can reduce end-to-end latency and improve energy and spectral efficiency, task offloading rates, and computational capabilities, and many more. Finally, reconfigurable intelligent surfaces. These are the key enablers for the smart propagation environment, significantly boosting channel gain diversity and improving the MEC performance of the system. RAS can help reducing the impact of obstacles and interference in wireless communication networks, improving the signal quality and reducing the latency. So, in summary, we can say that metaverse has enormous potential to change the way we interact with the world. But to achieve this potential, we need to utilize some of the other technologies like digital twin, MEC and RAS. Here is a motivation to our paper. Digital twin enabled metaverse architectures are a holistic digital mapping technology for intelligent resource allocation and network management. This means that these architectures can help us allocate resources more efficiently and manage our network more effectively. By using digital twin enabled metaverse architectures, we can improve our overall performance of our system and also MEC services. In addition to this, RAS aided communication can captivate better channel gain diversity in harsh environments. This means that we can improve our communication in environments that are typically difficult to work in. Overall, the consolidated DT and RAS enabled architectures and smart resource management can render improved MEC services in terms of minimized end-to-end latency, packet error probability, and energy consumption. This makes it is a compelling future research direction for MEC metaverse. In this slide, we'll discuss about the contributions to our paper. Our aim is to reduce the total end-to-end latency of the digital twin enabled RAS aided MEC URLC system while considering various constraints such as edge caching, task offloading policies, transmit power, and so on. To solve this problem, we proposed a deep reinforcement learning algorithm that can formulate the problem as an Markov decision process and uses the policy gradient optimization. That means our algorithm is designed to learn from its own experience to find the optimum solution by using a reward based system. Our simulation results show that our proposed solution significantly reduces the end-to-end latency and energy consumption compared to the scenario without RAS. Now we'll deal with the system model. We consider the RAS assisted MEC system where the set of M single antenna users communicate with the multi antenna base station for the task offloading purposes under the constraints on finite block length transmission. It is assumed that there is no line of sight operation, so we use RAS which has NR passive elements in it. The edge caching and the task computations are carried out by the edge server which is located at the base station. The respective virtual network is given on the right hand side and the problem called minimizing the end-to-end latency is carried out by the DRL model. Coming to the channel model, The effective channel gain of the mth user terminal can be given as Gm, which is equal to Gm Hermitian G1 phi G2m, where G1 and G2m are the channel gains of RAS to base station and mth UT RAS, and phi represents the phase shift matrix of the RAS. Gm represents the active receive beamformer at the base station. Now we define the signal to noise ratio for the mth user terminal, which is given by gamma m, which is equal to Pm G1 phi G2m square divided by Bm B W naught, where capital B represents the bandwidth of the system, Pm denotes the power transmitted by the mth UT, W naught is the single side noise power spectrum density, and Bm represents the allocated bandwidth coefficient of the mth UT. Under finite block length coding, the explicit relationship between the maximum achievable rate and the transmission latency for the considered URLC MAC system can be expressed by Rm and Tc naught respectively, where phi represents a transmission time interval and epsilon m represents the decoding error probability, and the Q inverse represents the inverse Q function, and Vm represents the channel dispersion. Now we define the DT architecture. Digital twin projects the physical world into virtual world by replicating the physical objects with 3D digital facsimils and companions. The proposed system is modeled by the DT, which is presented by DT is equal to m hat and k hat, which are nothing but virtual DT notations of the MUTs and K edge servers. The local processing rate at the mth UT is served by the DT is defined by DT MUT, which is equal to FUT and F hat, where FUT represents the processing rate estimated at the UT and F hat represents the difference between the real and the estimated value. Now we define the latency incurred in accomplishing a task at the mth UT by 6th equation, and the latency incurred at the edge server to perform the particular task offloaded by the mth UT by 8th equation respectively. Now we can define the edge caching enabled total end-to-end latency by 9th equation, and the total energy consumed at the mth UC consisting of the energy of the computation and communication by using E total, which is represented in the 10th equation. Now we define the problem formulation. The prime objective of this work is to minimize the total end-to-end latency among MUTs for the considered system by jointly optimizing the RAS phase shift matrix and portions of offloading task, allocated bandwidth at each users, and many more. So the constraints includes the 11B, 11C represents the maximum latency requirements and the maximum computation capabilities of the ES respectively, and the maximum energy consumption required at the UT is described by the 11D. The constraint 11E and 11F represents the quality of service for the uplink rate and the bandwidth allocation parameters respectively. Finally, the constraints involved in the RAS phase shift matrix and the maximum caching capabilities of the edge servers are represented by the 11G and 11H. The last constraint represents the uplink transmit power and the collection of offloading tasks and the processing rates, which are represented by P, A and F respectively. Here we go with the proposed solution. The optimization problem can be modeled by using the Markov decision process, and then we'll solve using DDPG based DRL algorithm due to its better learning and stability capabilities for stochastic time varying channels. Here DDPG represents a deep deterministic policy gradient, which is an actor critic network where the agent learns the optimum policy based on the environment and the network state and provides its outcome in the form of reward function and penalty for good and bad actions respectively. Here we consider the components involved in the Markov decision process. The first one is the state space. The state space has 4 components. First one is RM, which is nothing but the uplink URLC transmission rate, and the portion of UT locally executed task, which is represented by ρm, and epsilon n represents the required computational cycles, and uplink transmission power at the UT is represented by Pm. The action space is defined with respect to all the components involved in taking the actions, which is nothing but the ρm, B, phi m and PS and the processing rates at UT and ES respectively. Now we refine the reward function in terms of the minimizing the latency, which is given in the 14th equation, and the aggregated discounted rewards obtained from the set of state action values are represented by the 15th equation. To use DDPG to solve this particular task, we first initialize two deep neural networks, the action network and the critic network. The actor network takes the current state as an input and gives out the corresponding action. The critic network takes the current state and the action as an input and gives us its corresponding out value as its output, which is nothing but the estimate of the expected cumulative reward. We use a replay buffer to store the past experiences which are randomly sampled during the training to improve the sample efficiency. And we also define the policy gradient, which is given by 16th equation. And in order to update the critic estimation value, we need to minimize the loss function. And the loss function equation can be defined by 17th equation, where lambda represents the discount factor. Here we go with the proposed algorithm. First we'll initialize the actor network and critic network, replay buffer and phase shift matrix of the RAS and learning rate. For each episode from 1 to E, we'll receive the initial observation state from the digital twin. And we then for each iteration from 1 to T, we'll select the action AT and observe the reward function RT and the new state ST plus 1. We choose a minor group of D of transitions at random from the buffer, replay buffer, to maintain the execution transitions. We'll set yi with respect to 18th equation. Then we'll update q function by minimizing the loss function, which is given in the 17th equation. Then we update the policy gradient mu according to the 16th equation, and then we'll update the parameters of the actor and critic network by using the soft updates. Now let's deal with the simulation results and discussions. This table represents the simulation parameters which we have used. Here the figure 2 represents the convergence of the total end-to-end latency for varying number of users. So as number of users increases, the total computation complexity increases, which represents that the total end-to-end latency also increases. Besides, the proposed algorithm requires significantly less number of episodes for training. As a result, we can able to observe that convergence appears after 20 episodes only. Overall, the proposed scheme offers an effective resource allocation at the acceptable offloading decision even with higher number of users. The figure 3 represents the impact of the total transmission bandwidth on the system performance. As the bandwidth increases, the maximum number of the tasks that are executed in the specific time slot increases, which in turn results in decrease in the computational latency of the system. Increasingly, the considered MEC system initially undergoes high performance amelioration up to 8 MHz. However, the performance gain becomes nearly trivial with the gradual increase in the bandwidth. Further, we discuss the impact of the increasing base station antennas on the latency. The increase in the number of antennas increases the available phase shifters at the base station, which improves the channel gain diversity, and further it decreases the end-to-end latency. So overall we can say that increase in the available resources significantly increases the MEC performance. Figure 4 discusses the impact of the number of RAS elements on the system performance. The increase in the number of RAS elements improves the channel gain diversity. That means high beamforming will be attained, which improves the SNR associated with the computational offloading, and it decreases the latency. So the proposed beamforming design attains the better performance gain when compared to the random phase shift design. Moreover, we can able to observe that the RAS deployment for the MEC URLC system significantly outperforms the conventional MEC URLC system without RAS case. Conclusively, the optimum beamforming design with NR is equal to 256 renders approximately 35% better performance than the random beamforming. Moreover, it gives 58% better performance without RAS case. Figure 5 represents the impact of energy consumption budget for the optimum random and without RAS cases. For the given data size, the increase in the maximum allowed energy consumption at the users decreases for all the considered schemes. Obviously, the task offloading latency or the rate can be improved by the expense of high transmission power consumption. Primarily, RAS aided communication can ensure improved system performance under given URLC restrictions. Overall, the MEC system with RAS aided communication ascertains low latency while ensuring the low energy consumption and high reliability when compared to the without RAS case. Here we go with the conclusion of this paper. This paper proposes the DT-enabled RAS-aided MEC system for the URLLC, and it focuses on the minimizing the end-to-end latency by jointly optimizing the RAS beamforming, resource allocation, processing rates, and task offloading parameters. The resource allocation problem is modeled as MDP, Markov decision process, and solved by using the DDPG-based DRL algorithm. Simulation results shows that the proposed RAS beamforming outperforms the random beamforming and achieves 60% lower transmission delay and 25% low energy consumption when compared with the without RAS cases. Here are the references of this paper. And thank you.